Okay, chapter 15. Let me get my little toolbar, which I've lost. Okay, so that's about work and power. So let's recall Newton's second law. Sum of the forces is equal to dp dt. Let's assume a constant mass, and let's recall the definition of momentum, which is P is equal to mv. Let's plug that in, and we get sum of the forces is equal to m, which we can take out outside of the time derivative, times dv dt. Okay, what I would like to do now is I would like to take the dot product of this equation with the velocity. So velocity dot sum of the forces is equal to velocity dot m dv dt. Now remember that the velocity can commute with the sum because they have nothing to do with each other. It's like an integral. So I can write sum of v dot f, and I'm going to commute the force with the velocity. So I'm going to end up with sum of the forces dot v. Similarly, on the right hand side, the mass can commute with the v. So I end up with mass times v dot dv dt. Okay, so right now I'm interested in this term. So let's back up a little bit and let's look at this ratio, where it is understood that v squared is v dot t. So if I want to take the time derivative of v squared by using the chain rule, I end up with 2v dv dt, right? So let's solve for v dv dt, and we end up with I put my 2 on the other side, 1/2 of dv squared dt. So that makes sense. We start with the dot product. If this is dot product, this must be a scalar, and sure enough, this is a scalar, this is a scalar, and multiplied by a scalar, it's still a scalar. So let's plug this right there. We'll end up with sum of the forces dot v is equal to 1/2 m dv squared dt. Now let's recall that the velocity is dr dt. So if you plug that here, you end up with sum of the forces times dr dt is equal to 1/2 times the mass dv squared dt. Okay, now let's multiply everything by dt and let's integrate both sides. So my variable on the left hand side is dr, so I'm going to go from r1 to r2 of sum of the forces dot dr, and on the other side 1/2 m is a scalar, so I can leave it out of the integral, m divided by 2 integral of dv squared. So now my variable is v squared, so I can integrate from v1 squared up to v2 squared. Okay, let's integrate this first. We can do that easily. V squared, again, remember, is your variable, so it's like having x1, x2, x2 dx, except x is v squared, so this is nothing else than v2 squared. sorry about that, minus v1 squared, which is a scalar, which should make sense because we have a dot product on this side. So we can rewrite our result as 1/2 m v2 squared minus 1/2 m v1 squared, and we will define this quantity as the work, and the work done between position 1 and position 2. So the nice thing about the work definition is that you can either calculate it in terms of the force and the displacement. So this version implies that you know the sum of the forces, implies that the forces are a function of the position, and this implies that you know the path along which those forces are being applied to this object. But if you don't know anything about the force and you actually don't know the path, it's okay. You can use that definition. And this allows you to calculate the power by just evaluating the difference between technically the square root of velocities, which is totally independent of the path. Whoa, what is that? Sorry. Okay, so you have two versions for the potential, which is nice. So if the problem is giving you something in terms of the force, which has to be in terms of the position, then you can use this definition for the power, for the work, sorry. And if you don't know anything about the forces, but you know the final velocity, v2, and the initial velocity, v1, then you can use this version of the work. Now the only little problem is, with this, you have no information whatsoever concerning the time. So that's the only drawback. Okay, so this worked well for, say, a path which is a straight line between R1 and R2. Now we can do the exact same thing in a curvilinear path. So let's say you go from position S1 to S2 and you go along this particular path. We can do the same thing. So let's re-express our velocity in terms of the tangential component. Remember, there is only one component, ds dt times et. There is no normal component. Remember that the velocity is dr dt. Therefore, we can equate this with this, and we have dr dt is equal to ds dt times et. We can multiply everything by dt, and therefore dr is ds et. Now remember, here we can use and start from there again and replace our dr by ds et. So we can write sum of the forces dot dr is sum of the forces dot ds et, and this is equal to 1/2 m dv squared. So this is a scalar, we can take it out, so we can group this and this. So you have sum of the forces dot et times ds is equal to 1/2 m dv squared. We can integrate this the same way as we've done earlier. Now we integrate between S1 and S2. Sum of the forces dot et along the path ds is equal to 1/2 m, we integrate between v1 squared and v2 squared, dv squared. Now look, here we're taking the dot product of the sum of the forces with ET. Therefore, if you remember, that's how we define Ft. Therefore, this reduces to integral from S1 to S2. Only the tangential component of the forces, ds, is equal to our usual 1/2 m v2 squared minus 1/2 m v1 squared. And that's the work done. So the interesting and important aspect of this is when you go and travel along a path, you only care about the tangential component of the sum of the forces. The normal component will do no work, only the tangential. So if you have a path like this and your forces are like that, all you care is to calculate this component, the tangential. You don't care at all about the normal component. Only the tangential component does work. Now, if from this definition here, the sum of the forces happens to be a constant, then you can take it out of the integral, and you end up with sum of the forces in the tangential component is equal to times integral from S1 to S2. ds is equal to 1/2 m v squared minus v1 squared. So this is nothing else than sum of the forces in the tangential component times S2 minus S1 is equal to 1/2 v2 squared minus v1 squared. So remember, this is only valid if your forces are constant. And technically, if you're just looking at this, and if you want a graphical representation of this, this is nothing else than the area between the curve. So if this is your sum of the forces, the work is just going to be the area under the curve. Okay, so in summary, remember that the work is nice because you can either express it as the integral of the sum of the forces with respect to the r, or you can use curvilinear path, which implies that the force is a function of position and implies that you need to know the path to go from R1 to R2. But if you don't know any of this, you can use the other version, which is, if you recall, your definition of kinetic energy, 1/2 mv squared. So really it is nothing else than delta Ke, which most likely you've seen in Physics 170. This allows you to calculate the work done between velocity v1, initial velocity, and final velocity v2, without knowing anything about the forces applied to that particular mass m, neither the path. So you only care about the initial and the final. Okay, power. So units for work is kilogram, meters squared divided by second squared, or this is Newton, and this is meter, so the units for work has to be Newton meter. Power is nothing else than the rate at which work is being done. So by definition, power, which we'll use the letter P to designate, is du dt. If you're interested in the average power, what you need to do is use delta U over delta T. And delta U is the one we just derived here. and delta t is a big interval of time. So let's see if we use this definition of work with the force. We remember that the work can be defined as the integral from R1 to R2 of the sum of the forces times dr. Since P is du dt, then you can take the derivative with respect to time of the right-hand side. Now, in the case that the force is not a function of time, otherwise you can't do that, then you can bring this inside the integral, and so the power is the integral from R1 to R2, sum of the forces, dr dt, or the power is integral from R1 to R2, sum of the forces, times v, because remember, v is dr dt. And that's it.